Now in this section, it's time to learn about some selection rules and to finally start piecing together what pure rotational spectra look like. So if you remember when we were talking about the selection rules for vibrational transitions, for vibrational spectroscopy, we looked at matrix elements that looked like this. And in particular, we were able to write this as a dipole moment derivative times a single matrix element. And this dipole moment derivative, in the case of harmonic oscillators, told us that in order for a transition to be observed, the dipole moment for the molecule must change as a function of this of the bond shortening or lengthening, right? So basically, there has to be some bond polarity that has to be affected by the bond, and then this integral here told us that delta n could be only plus or minus 1. Okay, so we're going to look for similar things when we want to look at the selection rules for the rigid rotator. So in this case, as we'll see later on, the eigenstates for the rigid rotator can be labeled with two different eigenvalues. Actually, as we've already seen a little bit of this, but we will make it much clearer later on. So these are J, M. And then now the dipole moment in this case will in general be a function of both theta and phi, right? Both the direction that it's facing. And this is a matrix element with J prime, M prime. So with two other quantum numbers. To figure out what the functional form for this mu as a function of theta and phi, or in other words, the dipole moment as a function of theta and phi, to figure out what this ought to be, let's look at our diagram again for a rotating diatomic molecule. And imagine for a second that that M1, which is the lighter molecule, or the lighter atom as we're sitting here, is maybe slightly positively charged, while M2 is slightly negatively charged, which means that there's a dipole moment that points from atom 1 to atom 2. Okay, and the first thing we're going to do is we're going to simplify. So instead of looking at the total dipole moment, which remember is a vector, right, because the dipole moment will have components in the x, y, and z direction. So really this thing ought to be a vector up here. But we can simplify by just focusing on one component. And because this is sort of an isotropic system where we haven't specified, there's no difference between x, y, and z if it's just free space and there's no gravity, there's no ground, things like that. So we can pick any one and we'll get similar enough results. And so what we're going to do is just pick the z-axis. So instead we're going to look purely at this matrix element in the z direction. And again, we'll assume this is some general function of theta and phi. And so now what we need to know is what the dipole moment will be in the direction, or in the z direction. And from this diagram here below, because everything is fixed and there's no, whatever this charge is here, it's not going to change as the orientation changes. Only the way that it points will change. And so that means that this mu of z we can replace with a fixed dipole moment that we'll call mu 0. And then we just need to know its projection onto whatever axis we're interested in. And so we're interested in the z-axis at this point. And the z-axis can be written as cosine of theta here. Okay, so that means that this matrix element now, this more complicated matrix element reduces to, so we write this as mu naught times the integral of Jm cosine theta J prime M prime. Now again, by looking at these two pieces separately, we can come up with the two most important selection rules for the rigid rotator. The first is based on the mu naught, and this just says that for a molecule to absorb, the molecule must have a permanent dipole moment. Okay, so what this means is that molecules like HF or NO will absorb, but molecules like N2 or O2 will not have absorptions in the pure rotational spectrum. And the second part coming from the integral now instead of the scalar. So this tells us that delta J must be equal to plus or minus 1. There's one really crucial difference between vibrational spectra and rotational spectra, and that is related to the fact that this B parameter, the energy difference between two neighboring rotational states, tends to be much, much smaller for rotational states than it is for vibrational states. Okay, so we're talking for rotational spectra on the order of 1 to 10 wave numbers, which is the parameter for the energies, versus omega on the order of about 1,000 wave numbers for vibrational spectra. And so what this means is that whereas for vibrational spectra we could reasonably approximate that only the ground state was occupied at 300 Kelvin, that is absolutely not the case for rotational spectra. And the practical consequences of that are that in the vibrational spectra, you only ever really saw the 0 to 1 transition, or maybe if you have anharmonic effects, then you saw 0 to n. Whereas for rotational spectra, you're going to see 0 to 1, 1 to 2, 2 to 3, and so on, because all of these different states tend to be occupied. Whereas, again, in the vibrational case, you state 1, seeing the 1 to 2 transition didn't happen very much just because there are so few molecules that ever start out in vibrational state 1 at room temperature. Okay, and again, using this condition that delta J is equal to plus or minus 1, we can now derive at what energies you'd expect to see the transition. So what energies you'd expect to see show up in a rotational spectrum, in a pure rotational spectrum. And these will be given by delta E of J is equal to E of J plus 1 minus E of J, which is h bar squared over 2I, and then we'll combine the integer parts of this. And so plugging in the J plus 1, you have J plus 1 times J plus 2 minus J times J plus 1. Just as a recap, this is using that E of J is equal to h bar squared over 2I times J plus 1. Okay, so now if you notice that both of these terms in here have a J plus 1, and so we can factor this out and turn this into h bar squared over 2I times J plus 1. And then what we have left in the first term is J plus 2. And then in the next part, there's J left over, so we have minus J. Okay, and now this will simplify straightforwardly to just h bar squared over I times J plus 1. Or in other words, 2b J plus 1. So let's see what this looks like as a spectrum. So if we look at our energy levels here, so this column here is labeling the J value. And so at this one we'll have, so E of 0 would just be 0. E of 1 should be 2b. E of 2 should be 6b. E of 3 is 12b. And E of 4 is 20. Okay, so these are showing you the different energy levels. And remember, what makes this very different from vibrational spectroscopy is that you will actually be able to see all of these different transitions. You'll be able to see the transition from 0 to 1, from 1 to 2, from 2 to 3, and from 3 to 4. And actually the other way around as well, so you'll be able to see 3 to 2, 2 to 1, 1 to 0, and so on. And what we just showed before is that the energy of these transitions is 2b times j plus 1. So the 0 to 1 transition, right, the energy difference between states 0 and 1 will show up as 2b here. The transition from 1 to 2 shows up as 4b, and so you end up with this thing here. The transition from 2 to 3 is 6b. Okay, so now what you get when you have a pure rotational spectrum is you have this series of evenly spaced lines ranging from, so you won't have a transition at 0, your first transition is at 2b, and then there's one at 4b, 6b, 8b, right? So you have these evenly spaced lines separated by 2 times b, or 2 times the rotational constant. And all of these different lines are coming from different initial j values, right? So the 6b transition, for instance, is coming from the transition from j equals 2 to j equals 3. And the reason that you can see all of these, just to be painfully clear, is that you have many different j values can be occupied at room temperature, which stands in direct contrast to what happened for vibrational spectroscopy, where normally only at most the ground state was occupied at room temperature. Okay, so those are the fundamentals of pure rotational spectra. Okay, now the last thing we'll do in this section is to quickly look at what information this tells you right away. And so we're going to imagine that we can measure, or that we have measured, the rotational spectrum of HCl. And in particular, this corresponds to a series of lines separated by 6.26 times 10 to the 11 hertz. Okay, so previously what we showed is that the energy spacing between two consecutive levels is delta E of j is equal to 2b times j plus 1. So that means if we're witnessing a series of lines separated by 6.26 times 10 to the 11 hertz, then this number here should be equal to 2b. Or here we're just using the fact that hertz is equal to 1 over seconds. All right, so this actually is already a little wrong, you can tell, because the units don't quite match up, right? So we have energy on the left and we just have frequency on the right. And so before we can do anything with this, we need to convert this frequency into energy. And this is the frequency of the light, and this is really easy. We just multiply this whole thing by h. And now we look at what this all is equivalent to. So we replace 2b by its definition. So this is 2 times h bar squared over 2I, and this is equal to 6.26 times 10 to the 11 hertz h divided by s, so Planck constant divided by s. So we can simplify this further. So for one, take out these constants, and also use the fact that moment of inertia is equal to mu times L squared, where mu is the reduced mass and L squared, or L is the distance between the atoms. So now what we have actually is an expression where the only unknown is the distance, right? So we know h bar mu we can compute just based on knowing the identities of the atoms. And this is a measurable, and then this is Planck's constant. And so it means that we can solve this data for L squared. And this is a little bit redundant because we have h bar and h in the same equation, so we can simplify by turning h bar into h over 2 pi, and this will turn into Okay, and then I'm not going to go through the details of this on this video, but I encourage you to go back and check my math on this. Okay, and then you can solve this for L, which is just 1 over 2 pi square root of h over mu times 6.26 times 10 to the 11 per seconds. And if you plug this in for using HCl and this data here, then what you get will be 1.29 times 10 to the minus 10 meters, which is equal to 129 picometers. All right, and so this is pretty cool, right? So this means that just by looking at the rotational spectrum of a diatomic molecule, we can basically directly compute the bond length. All right, so just by looking at the spacing between different peaks in a rotational spectrum, we can figure out what the bond length is. So this is for a pure rotational spectrum. In the next section, we'll start talking about what happens when vibrations also accompany rotational transitions.